Let's practice uniform circular motion by considering a model train set. Here's the circular set of tracks, and here's the little tiny train. Let's mark the x direction and the y direction on here. And the idea is that if we know the radius of the train track, we ought to be able to reconstruct what the train is doing as a function of time as long as it is uniform circular motion. So the train goes around the track. Very exciting. You can imagine that if we're given even a simple quantity like the period of the train's circular motion, so imagine that we're told that it takes 8.00 seconds for the train to go around the circle once. That's the train's period, and we'll use a capital T for that. You have to be careful. Lowercase t means an arbitrary time. Capital T is a period for something undergoing circular motion. We also said that we know the radius of the circular track, 1.50 meters. Let's imagine that we want to calculate quantities like the angular frequency, omega, maybe the speed of the train, v, and maybe we want to know its position at some later time. So I picked an arbitrary time, 86.50 seconds later, after the train started, where I showed you basically with its front right under the x-axis. Then we want to know its position at some later time. Well, we have some equations to help us. One set of equations relates the angular frequency, the period, the speed, and the radius of the circle. The other equation is simply the position vector for something undergoing circular motion. Okay, so let's remove the drawing of the train, and let's start with the angular frequency. So that's pretty simple to solve. The angular frequency is 2 pi radians divided by the period in seconds, so we just plug in the period of 8 seconds. We get that the angular frequency is 0.7854 radians per second, which to 3 significant digits, 0.785 radians per second. Let's write that over on the left. The next quantity we'll calculate is the speed. There's a simple equation for that too. The angular frequency is the ratio of the speed to the radius of the circle, so let's just solve that for the speed, and we'll plug in our values. We know r, we know omega, so we do that, and the speed is 1.178 meters per second. You may have noticed that the radians that were in radians per second and omega went away when we calculated the speed. Remember, radians really represent a ratio, which is why they're a weird unit that can sometimes seem to disappear and appear randomly. You just need to carefully track what quantity you're talking about to make sure you cite the right units. Okay, so the speed is 1.18 to 3 significant digits meters per second. Let's write that on the left. Now we're going to go through and calculate the train's position at time 86.50 seconds. Okay. So after that amount of time, the first thing we can figure out is just how many times has the train gone all the way around the track? How many complete circles has it filled out? Well, the number of complete circles will be this ratio, the time to the period of the train's circular motion, but you have to be careful because generally speaking, that won't be a whole number. So if you want the number of complete circles that have been finished, you ought to round down to the nearest whole number. Let me show you. So in our case, that'll be 86.5 seconds, the time, divided by 8.00 seconds, the period of the train's circular motion. Divide those two and you'll get a number a little bit bigger than 10, but we round down to 10. So the nearest whole number lower than that is 10. That's 10 whole circles. That's the number of times the train's gone all the way around the track. But if we want to know the train's exact position at time 86.5 seconds, then we have to be a bit more careful. We should consider the position vector. So we know it's gone around 10 whole times, but where is it after going around 10 times? Well, the position vector at that same time, 86.5 seconds, is given by that expression over there on the left in vector form. We know A, we know omega, and we know t. You may remember in this form, A is really just referring to the radius of the circle. It's strange notation since we called that r over there. You'll see later on when we do oscillatory motion, there's a reason that they chose the variable A. We'll get to it. But we know that value. A is 1.5. Omega was 0.7854 radians per second. Using a little more precision so we have an accurate calculation, and our time was 86.5 seconds. So we put all of that in, making sure to keep our I-hats and J-hats straight, and we also make sure to set our calculator to radian mode so that we get sensible answers here, and we find that our position vector is 0.574 meters times I-hat minus 1.39 meters times J-hat. That's the position vector. So that is one way of answering where's the train at 86.5 seconds. You may also want to know in terms of angle where the train is, because if you think about it, for uniform circular motion, really you can specify its position entirely in terms of an angle as long as you know the radius of the circle. So what would that angle be in this case? Well, we've dealt with angles and vectors before. If we draw out an xy set of coordinates, well, the x component of our position vector is positive, the y component is negative, so we expect a position vector that points down and to the right. And we can decompose that into Rx and Ry vectors. And then I'll mark this little angle in the corner there, the upper left corner of that triangle. If we figure out that angle, then we can describe the position of the train. So the tangent of that angle, which I'll call phi, must be the ratio of the length of the opposite side of that triangle to the length of the adjacent. So that means in this case, the tangent of phi is 1.39 meters divided by 0.574 meters. The units cancel. Solve for that using the inverse tangent, and you get that phi is 67.6 degrees, meaning that if we had measured the angle theta, which goes counterclockwise from the positive x direction, remember, the way we've defined phi and theta in the past is that the two of them have to sum to 360 degrees, well, that tells us that theta is 292.4 degrees measured counterclockwise from the positive x direction. So if we're asked about the position of the train at time 86.5 seconds, you could say, well, for one, its position vector is this, and its angle counterclockwise from the positive x direction is that.